last talk for today, but it looks to be the most beautiful in terms of slides, at least so far. So, Wendy?
Yeah.
Go ahead.
我们滚成一团。
Hello, thank you guys. I'm Wenli Zhang, a PPMC of the Apache ECharts incubating project. And thanks for joining me today with the web-based interactive big data visualization topic. So big data has been a hot topic over the years. And how big are we talking about? What's the magnitude of the data can we render interactively on a web page? The number we are discussing about is tens of millions of data pieces. Well, what does that even mean to have tens of millions of data in a single chart? To make it easier for you to understand, let's take the example of a Full HD monitor whose resolution is 1920 to 1080. The overall pixels are about 2 million. So, for a chart with 10 million data pieces, it means that on average there are 5 data pieces in a single pixel. I will explain why this is necessary and how we make this possible next, but first let's have some background information. I'm Wenli Zhang from Shanghai, China, a PPMC of the Apache ECharts incubating. I joined Baidu 3 years ago and have been working on the ECharts project ever since. I'm also an active contributor in the open source world. I've made several visualization-related projects like the low-poly image and the video rendering on the top left side. You may also check out my GitHub profile to find out more. Apache ECharts Incubating is a JavaScript visualization tool and more. You can create so many cool things with it, like 2D and 3D maps, interactive graph charts, fancy animation of the globe, radar charts, large-scale scatter charts, circular tree charts, sunburst, thin river, and so on. It renders charts in web browsers so that visitors can interact with them and find more interesting results. ECharts was originally a project inside our company Baidu. 7 years ago, an engineer created a chat tool to solve the problem relating to his job. He found that this could also help many others. So after half year's improvement, he made this open source on GitHub under an organization of Baidu. That was back in the year 2013, and the ECharts project has enhanced extensively, and the community has grown much bigger. So in the year 2018, we started being incubated at the Apache Software Foundation. ECharts provides a selection of extensive chart types, which enables users to find a quick way to implement chart requirements of all kinds. And even if you want something else, the custom series that ECharts provides gives you the ability to decide what your own charts look like and implement it so fast that you can hardly imagine. We also have many community-created chart types that may serve as an extension, so that other people with similar requirements can use the chart you create. The second feature of ECharts is that it provides a cross-platform solution with which you may write code once and run everywhere. This includes different rendering mechanisms like Canvas, SVG, and VML, each of which specializes in certain conditions. For example, Canvas has an excellent performance for rendering big data, while SVG usually consumes less memory. So on platforms like some low-price Android devices, SVG may probably have a better performance. ECharts provides responsive design mechanism which works pretty much like the CSS media query, so that different chart layouts can be applied on PC and mobiles. The community provided a large number of ECharts extensions to other programming languages, so that you may find a way to use ECharts even you don't use JavaScript. Another thing worth mentioning is that ECharts provides powerful interactions, which work out of the box. You can use these tools to make your charts more interactive and powerful. And the best part of it, you don't need to write too much code to make all these happen. When we went to share about big data rendering topics 2 years ago, we were talking about hundreds of thousands of data. And today, we are talking about tens of millions of data on a web page, which is hundreds of times faster. Now I'm going to introduce in more details about how we made this happen. You may wonder why big data should be rendered in the front end. Instead, we could, with Plan A, render an image in the back end and transfer the image to the front end. Or with Plan B, pre-calculate the data and reduce the amount of data to be transferred to and rendered in the front end. But these back-end solutions come at a great cost. First of all, users can hardly interact with an image or zoom in to see more details with pre-calculated data. Second, reducing the data amount by brute force usually results in less detail, so the visual result can be bad. Next, it requires extra coding and computing resources to reduce the data amount in the back end. On the other hand, if we render the big data in the front end, it provides a better experience to the viewers who can zoom in the canvas and get to know more details without network delay. The basic workflow of web-based visualization is usually for the web browser to request the server for data, and then do the rendering job on the browser side. This may seem to be easy, but it's in fact a challenging job to do. The challenge lies mainly in the conflict of the need to render back data and the limitation of web browsers, which includes network, memory cost, and the responding time of web browsers. To tackle with this problem, we designed ECharts in this workflow. ECharts uses a JSON-like option to manage the chart configuration, in which the raw data is included. When the option is given, we then create or update models based on whether this is the first time an option is given. Models contain settings and normalize the data with multiple dimensions. Then the data to be rendered is restored, considering components like data zooming. Next, coordinate systems are created and updated based on the range of data. Then we lay out the data with given chart type and do visual coding like mapping the data value into the color or size of data items. After that, it generates rendering instructions to render shapes or update styles. But ECharts does not do the rendering job by itself. Instead, it uses cRender, which is a cross-platform rendering engine doing all the real rendering job. cRender provides a unified API for rendering with Canvas, SVG, and VML, so that we don't need to consider the different implementations on these rendering engines when writing code in ECharts. When user interacts with the chart, all actions are dispatched programmatically. The data is updated and rendered again. From the experience of developing ECharts, we came up with a solution to speed up the rendering process with following 4 aspects. The first is called the user scenario-based approach. Basically, this means we need to find the bottleneck of a given scenario and enhance it. But this is easier said than done, just like the joke of teaching you how to draw. So I'm going to use 2 examples to demonstrate it. In the first case, there is a line chart with 500,000 data. If the grid width is 1,000 pixels, then this means there are 500 data in a single pixel. Apparently, we can hardly find the difference unless the chart is zoomed in. So the solution is to reduce the sampling rate to 1 out of 500 perhaps. And when a user zooms in an area, the sampling rate is increased so that the fewer data can be rendered again. In this way, the user will hardly see any difference, but the amounts of data rendered are always 1,000 rather than 500,000. Furthermore, ECharts provides the policy of deciding the value to be rendered out of the 500 data. You may choose to use the minimum, maximum, or average of the 500 data, or pass through a callback function to do the reduced job by yourself. Another case is about the candlestick chart. For candlestick charts, a typical data looks like the graph on the right side, where you have one rectangle showing the open and closed values, and a line showing high and low values. When there are too many bars to see clearly in a chart, it can save half of the rendering time if we render only the line without the rectangle. The pros of the user scenario-based approach is that it usually can achieve a magnificent improvement with very low cost of development. As the examples of the previous cases, the extra coding work lies only in deciding when to filter the data or reduce the graphic to render. It can have very low impact on the visual result because viewers can hardly find any difference. But on the other side, the solution is limited to certain scenarios, so that the way to improve line charts may not also work for scatter charts. The second approach we'd like to share is code structure based. Sometimes we need to change the code structure or code expressions to enhance the efficiency. Let's take bar charts for example. When rendering each bar, we need to set the canvas view style and draw the rectangle. If this is a bar chart with big data, we may merge these bar rectangles into a single compound graphic element. In this way, the canvas view style is set only once at the beginning, and draw functions are called multiple times. Another case is about garbage collection. We can see there is a GC time of 5 milliseconds, which seems to be quite short. But if we think in this way, that a 60 FPS system requires each frame to be less than 16 milliseconds, then a 5 milliseconds of GC time will become unacceptable. And even for a 20 FPS system, 5 milliseconds seems to be long enough. So yes, we don't have time for the garbage collection. First, we need to be clear about what garbage is. In our daily life, garbage is the thing we no longer use. Similarly, in the scope of JavaScript, it means objects that cannot be reached anymore, where objects may be variables, functions, and so on. JavaScript has a global variable called window. All other objects are referenced by it either directly or indirectly. After some while, for example, when we go outside of a function, then the inner variables become unreachable. So they are called garbage. Just like most of us, we do not throw away garbage all day long. Many of us may throw it only when the trash bin is full. Similarly, we do garbage collection only when we find there is no space for new allocation. Unlike low-level programming languages like C, JavaScript developers don't think of garbage collection in most cases because it's automatically taken care of. But for performance-related issues, we need at least to have some idea of GC. So how to do this GC job? When we look at the lifetime of objects, we may find an interesting result, that most of objects die young and occupy limited space. For example, if the program goes out of a function, then the local variables defined in that function die. On the other hand, those who do not die young tend to live a long life and occupy more space. In V8 engine, these are called the young generation and the old generation. They have very different policies in managing memory and sweeping when out of space. All objects are of young generation when created and become old generation when failed to release afterwards. As we said, the young generation dies young and occupies limited space. So V8 uses a space for speed policy to reduce the GC time. In each moment, there is always an extra space reserved for the young generation. When there is no space for new allocation and we need to do the GC job, it copies the root node, which is the window, to the new space called toSpace. Then doing a breadth-first search from the root node and copies the living nodes to the toSpace. After that, swap toSpace and front space so that the new toSpace is reserved for the next GC job. And now we have space for the new allocation. The situation with the old generation is much more complicated, and I don't wish to bore you guys into too much details since, there's already so few people here. The most important difference we need to know about the old generation is that it doesn't have an extra space for copying job, because the old generation occupies more space and does not tend to sweep frequently. So, without the speed for space, GC of the old generation takes a longer time. As a result, the most time-consuming part of GC is with large objects of old generation. That is, large objects that are not released for a long time. So, to avoid them, we can either prevent them from getting old or avoid using large objects. To avoid them from getting old, we can release them early or reuse the older ones. To avoid them from being large, we can use typed arrays to reduce memory cost, avoid reallocation, and avoid sparse arrays. But on the other side, we have to manage the arrays by ourselves and do all the low-level operations. In conclusion, changing code structure and code expression can help to some extent, but it brings much damage to the code structure, readability, and robustness. So take this approach only when you find there is a performance problem and use it only when necessary. The third method is based on perception. That is to say, if we cannot speed up anymore, at least we can let the visitors believe so. This may sound a little crazy, but it's actually very efficient. The general idea is to render as much result as possible and respond to user interactions while it's still rendering. Before introducing progressive rendering in ECharts, this is what you get when rendering 300,000 data points. The bars in the bottom show the duration when UI is blocked. If it's red, it means the blocking time is too long. As you can see from the video, the interaction of zooming in is not responded until several seconds later, and the overall experience is very bad. ECharts version 4. That is to render part of the data in each frame and shows the result gradually. This experience can be improved greatly. Before ECharts 4, the data is processed and rendered all together. But in ECharts 4, we split the data into chunks, so that each chunk can be rendered progressively. The size of each trunk can be adjusted. For example, if you have a 100,000 data series, you may split it into 100 frames, so that each of which have 1,000 data. And then the full picture will be rendered after 100 frames. But the viewers won't find the rendering time to be long because it's updated all the time. One problem with progressive rendering is that it takes several seconds to complete the full rendering job. So the user, if he moves the canvas, it will be cleared and rendered again. With each move, the canvas is cleared totally, so it takes another several seconds to render the result. This may provide a bad experience because users won't expect it to be cleared and re-rendered, since they are just moving the canvas around. With WebGL, we can set a viewport when the user moves the map so that the previous problem can be fixed and the user can have a smooth zooming experience. The perception-based approach helps improve user experience by giving instant feedback and continuous progressing, but it usually causes a great change in the architecture. For example, we largely changed the pipeline of ECharts to achieve the result I introduced earlier. So use this approach only when you are rendering big data. The last one I'd like to share about is data loading, which is largely related to the progressive rendering. For example, if we use JSON to store the 100,000 data of that map example, the file size will be about 100 megabytes. Even if gset, a 40 megabyte file is still too large to transfer, before the 5G network, we can store the data array in binary format so that the file size will be 20 megabytes. Then we can split the data into 32 files, and now every file is less than 1 megabyte. We can use the progressive rendering introduced previously to load one file and render that part of the data. When splitting the data, however, it is important to split them randomly. Otherwise, you may probably get something like this case, in which the loading data doesn't seem to be an animation. Instead, users may get anxious while waiting for the whole data to be loaded. The data loading approach is pretty much like the perception approach, only that it's dependent on the progressive rendering. At the end, I wish to talk a little about the challenge ECharts faces and our incubation under the ASF. One of our most severe problems is that ECharts has a limited contributor number as compared to its user number. This is quite dangerous because it means a maintainer has to serve for thousands of users, answering their usage questions and fixing their bugs. We're still trying our best to encourage more people from the community to help and make it a healthier project. The second problem is that it lacks international users. So how many of you guys have heard of ECharts before? Could you please raise your hands? Okay, that's 1/4, I suggest. And ECharts has the market share of about 70% in China, but not so well known internationally. We wish to make it known and used by more people all over the world because we believe ECharts can save the time of many more people. So you are very welcome to join the community and have fun with that. We have learned a lot of things since the incubation, And the most important one is to be more open. Although we have been open source for many years before joining ASF, ECharts was maintained by only a small group of people inside the company. And perhaps we didn't quite get used to the Apache way until a few weeks ago. But now we are discussing more and more things on the mailing list and let the community know what's going on. Sometimes we may find the offline communication to be so tempting because it's really efficient to do so as compared to email discussion. But the mailing list is an important way to let the community know about what's going on, and that's the very first thing we should provide if we wish to get help from the community. And you are welcome to subscribe our mailing list to get notice and join the discussion if you are interested. The second thing is we are adding more documents for everything. Not only about how to use ECharts, but also how to get help, how to contribute, how to fix the problems, and so on. The third thing is to appreciate the help and provide more convenience to the community. This will make the community become more friendly and eventually provide more help to the project. We're still learning hard on the Apache way and trying to make our project better, so please join us and let's make cool things together. Thanks, that's all of my topic. Thanks for listening. And if you have questions that you don't have time to ask today, you may send me an email. I will be very glad to help you.